Welcome to week 4 of the live session for fundamentals of convective heat transfer. And myself, Dr. Prasad. We'll wait for a couple of minutes for a few more students to join and then we'll get started. Get started. So this week of lecture videos discusses about another method. So in the last week, we discussed about similarity solution, where we solved the boundary layer equation using exact methods. And in this week, we will discuss another type of method, which is an approximate method called integral method. So for that, we will start from where we stopped in the last week, where we discussed the concept of displacement thickness. So let's say we have a boundary layer flow. We have a boundary layer flow like the follows, where we have a uniform inlet stream and a profile u of phi. This is my y direction and this is my x coordinate. So the concept of displacement thickness starts when you apply the control volume analysis. So first we can maybe make a control volume for this surface, so something like this. So why am I considering a control volume like control surface like this is essentially because now I want to do two things. One is to calculate the mass flow rate to the control volume, and second I want a momentum balance for this control volume. So in order to do the mass balance, I have to make sure the control surface is such a way that there is no net mass flux through that particular interface. It will be only through this surface and it will only be through this one. So if we do not know what this surface is going to be, but let's say the surface is such that there is no net flux, net mass flux through this particular surface. So that flow is only happening in this direction. So now if I were to write the mass balance for this in this, let's call this as delta star, which we will later call displacement thickness. And this as our boundary layer thickness delta. Then our control volume analysis will say that the net mass flux in should be equal to the net mass flux out, which will give us the net mass flux integral rho u dy. If you are writing at the inlet, so that will be rho u is basically u infinite dy, and the length of this is 0 to delta should be equal to integral rho u dy 0 to delta plus from delta to delta plus delta star we have again after the delta the velocity will be equal to free stream velocity, so that is rho u infinity times dy. So this gives us rho u infinity times delta is integral rho u dy plus rho u infinity delta plus delta star minus delta is delta star. And what we are trying to do here is find the value of delta star, which I'll again come to in little time why we need this particular quantity. So delta star can be written as delta minus integral. Again, this is a flat plate, so we are assuming u infinity is constant. Along the x direction, free stream velocity is not changing. This we can rearrange to write this as this is our displacement thickness. From here, we will also extend the this we got from mass balance. Now we will also do momentum balance, from which we will get the momentum thickness, which is the most important quantity that we'll be using throughout these problems that we'll be discussing today. So if we apply the momentum balance across the same control surface that we have before, the net force acting on this surface is again same as before, equals to the net mass outflux minus net momentum outflux minus net momentum influx. So that will be integral 0 to the net outflux is 0 to delta plus delta star. The momentum is given by rho u times rho u is the momentum vector times u times dy. This is how we apply the control volume analysis. Minus influx 0 to delta. We have only u infinity throughout, so that is this quantity, where the net force that we are going to experience by this entire surface, the control volume, is from the bottom of the plate or whatever this wall or surface that we have here, is going to give us the net force on the fluid. So that force is represented as, because it is in the negative direction, like the air is pulling the plate in the positive x direction, which means the plate will pull the fluid in the negative direction. So that will be minus rho u infinity square times delta double star. This delta double star is what we call momentum thickness, which is something that will be useful for us in this week. So in the lecture videos, the professor has actually used a notation theta, but I'm just changing the notation because we will use theta for temperature. Just to avoid confusion, I'm using delta double star for momentum thickness. We'll write it here. The displacement thickness is delta star and momentum thickness is delta double star. So this gives us from 0 to delta, this will be rho u square plus from delta to delta star, this will be constant. So that will be rho u infinity square times delta star minus rho u infinity square times delta. And we already have the value of delta star with us. So we can substitute that back in this equation and then you can simplify and get an expression for delta double star. And wait for a couple of minutes. Can you please try this out and tell me the value of delta double star from this expression? So if you simplify, you get an expression like this. So these are the two main equations that we will be using. First, we will start from here and then we will discuss momentum integral method. And then we also discuss the similar to just like displacement thickness and momentum thickness. This is from mass conservation. This is from momentum balance. Now we can also do energy balance and we will get one more equation. So if you do the same for energy balance, we have the net heat flux given by from 0 to delta plus delta star. We'll be having rho times u times. For energy balance, the quantity that is being conserved is enthalpy, which is given by Cp times T. This we have discussed in the first week of lecture videos. Minus the net incoming energy flux is 0 to delta rho u infinity free stream velocity times the specific heat times the free stream temperature. Now again from here it is same as before. So 0 to delta, this will, I can take rho Cp out, and this Q is basically the net heat flux, that is the, we'll get to that in NPTEL 2. So we have rho Cp 0 to delta ut dy, and from delta to delta star. Here is again where we have to assume something so that we do not know event, because if we assume Prandtl number to be approximately 1, then delta will be equal to delta t. And in that particular case, we can write u into t as u infinity into t infinity, because after delta, both are reaching their free stream values. This is the assumption I'm making here. So if it was not the case, for example, if Prandtl number is greater than 1, then delta will be greater than delta t. In that particular case, beyond delta, since delta is greater than delta t, the t would have been reached t infinity much before delta. So this will split into 3 terms: 0 to delta t to delta, and delta to delta star. So accordingly, this keeps changing. The details of all of this is already been covered in the lecture video. So I'm kind of taking the most simple case just to give you an understanding of recap of the basic idea of what is being discussed in this lecture videos. So from delta to delta star, we have this, and the other term is 0 to delta. So again, we can do the same method as before. So this would give us minus delta will you can solve. Maybe I'll wait for a minute here. So you can solve and tell me what the expression you are getting. We'll have to first substitute the equation for delta star. And then do the math. So once you do that, you will get an expression of the kind where the q dot is given by we call this theta star. Just like momentum thickness, displacement thickness, we have this additional quantity which we call theta star, and that we can obtain from this. So if we solve for theta star, we get as I said, theta is the non-dimensional temperature that we'll be using, which is given by we have to non-dimensional theta in such a way that at the wall the value should be 0. So I'll be taking T minus TW. At wall, T will be temperature will be equal to the wall temperature, so this will be 0. And at free stream, it should be equal to 1. So I'll have to take T infinity minus TW. So at free stream, this will be equal to 1. With this theta, we have another number. So now we have 3 different numbers: displacement thickness, momentum thickness, and similarly for the energy boundary layer, we have one more thickness value. So the use of these values is now in the approximate method when we use integral method. So first one is momentum integral method. The idea here is fairly straightforward. You assume like you have a boundary layer, you consider some small length delta x in that, and the net force acting in this on this particular layer is given by the shear stress times delta x, and this should be balanced by the total shear stress that we are having, which is also given from the momentum thickness. So as you see before, the momentum thickness is defined in such a way that the net force acting on it is given by rho infinity times the momentum thickness. So all we'll be doing here is for this differential volume, we have rho infinity times for that small volume, whatever is the change in the momentum thickness that we are going to have. In the limit that delta x tends to 0, we will be having tau w as rho infinity square d delta double star by dx. So the main idea in momentum integral method is first we will assume a particular profile of velocity. So we use the similarity form. So you will assume u by infinity to be some function of y by delta. This is again coming from the fact that boundary layers follow the similarity transformation, which essentially means they do not have any memory. If you know the velocity at any given point, you can find the velocity at any other point, independent of where that is starting from. So that is the main point that we take away from this. So first you will assume a given velocity profile. And once you assume the profile, the next step is to calculate the value of tau w, which is given by mu times du dy at y equal to 0. So from the assumed profile, you calculate tau w. And once you have the tau w, you can and delta double star, we can calculate from this expression. Delta double star is given by this expression. So since u by infinity profile is already known, you can directly substitute in this and get delta double star in terms of delta, which itself is a function of x. So once we have these two quantities, we can substitute in this equation. The only unknown here will be the delta. So this tau w will be a function of, this will be a function of delta, and this will also be a function of delta. So we have one unknown and one equation, and that one equation is this momentum integral equation, which you will solve and you will get an expression for delta. Now similar to momentum, we also do an energy balance equation and we get the energy integral method. So same as before, instead of the shear stress, we will do an energy balance. So we'll have the net heat flux times the differential element that we are considering, given by the energy thickness number, which is rho Cp u infinity times Tw minus T infinite times theta star. So in the limiting case, we'll have Qw by rho Cp as d theta star by dx. Here also is the same thing. You will have to assume a profile for theta in terms of y and delta. So once we have a profile for theta, we can calculate Q double prime, where Q double prime is minus k times del T by del y at y equal to 0. K is the thermal conductivity of the fluid. From this, you can get an expression for T, and you can solve this and get the expression for Q double prime. Once we have the expression for Q double prime, this will be a term which will be only a function of delta T. And similarly, theta star is given by this expression, which is also a function of delta. So again, we have one unknown, one equation. We can solve this. So as I said here, in this derivation, I've assumed delta equal to delta t. So since both of them are equal, we do not need to solve two times. But in general, delta and delta t are not equal, and the Prandtl, we have the relation between delta and delta t given by, if Prandtl number is not equal to 1, then we have delta by delta t scaling as Prandtl to the power half. So from this, we can substitute that back, and so we'll be having two unknowns, that is delta and delta t, and we have two equations. One is the momentum integral, the other one is energy integral. So two unknowns, two equations. Once we solve them, it will be much better when we solve problems. Let's take some problem first. First, let us understand how to calculate displacement and momentum thickness. This is a simple problem where I'm assuming the velocity profile of this particular form. U by u infinity is 3 by 2 times y by delta minus half y by delta cube. Compute the shape factor, where shape factor is defined as the ratio of displacement to momentum thickness. Wait for a couple of minutes, we can solve this. So I'm just writing the equations here so it will be easy for you. The momentum thickness, first the displacement thickness is given by integral 0 to delta 1 minus. This is an estimate of the mass deficit. This is displacement thickness. And then we have momentum thickness given by the momentum deficit. And shape factor, H, I'm calling it as H, is given by ratio of, sorry. And H is given as the ratio of displacement to momentum thickness. We'll talk about what the value of which implies physically also, but first let us solve this problem. Carry out these integrals in much easier way. You can also think of this as some function of eta, where eta is y by delta, similar to what we did in last week. If you call this as eta, then u by u infinity, you can call it as f of eta, is given by 3 by 2 times eta minus half eta cube. And if you transform this integral, you'll essentially get delta star by delta as 0 to 1, 1 minus f d eta, and delta double star by delta is 0 to 1, f times 1 minus f d eta. And then h is basically the ratio of these two quantities. Delta will anyway get cancelled, so we can directly calculate. So this is a straightforward integration that you have to. I'm getting this as 3 by 8, and this is coming as around 32. And from this, when I calculate h, getting around 2.69. Confirm if you're also getting the same values. Okay. Same answer. The physical significance of this particular number is if the profile would have had a different shape. Instead of this, you can also try with a different linear profile, or you can try a parabolic one, like a quadratic one, and then try to calculate the h value. And then later, when we solve turbulent boundary layer equation, then also we can do the same thing. Then also we'll assume a particular profile and calculate h value. And we will see that as the profile moves from the laminar to the turbulent region, the value of the shape factor changes. So when you are doing an experiment, you do not know what the you can actually measure the velocity profile at any given point, and from there you can calculate these integral values. You can calculate the displacement and momentum thickness, and from there you can calculate the h value, the shape factor, and you can use that to say which like roughly, not exactly, but it can give you an estimate of whether you are in the turbulent region or in the laminar region. There are other ways also to detect laminar or turbulent, but this could be one way. So this tells you what is the kind of velocity profile that you are dealing with in your particular case. Are there any questions in this? This is normal integration, so I think there are no questions in this. Okay. Yeah. And this is the common thing, like if you're applying for an exam or something, these are kind of a standard questions that you can expect where you'll be told to assume a particular velocity profile. Usually they have given you the velocity profile, but even in the latter case, I have given you the velocity profile. But sometimes you can also be asked to assume a velocity profile of some polynomial. So you start with some polynomial, and then you have to apply the boundary conditions that velocity has to be zero at eta equal to zero. We need u to be zero. I'll call this f from now. At eta equal to zero, we need f to be zero, which is the no slip condition at the wall. And eta equal to one is the free stream. F should be equal to one. And we can also use other conditions that at eta equal to 1, there shouldn't be any shear. And similarly, we have one more condition that eta equal to 0, the double derivative equal to 0. The second condition is coming from the, if you see the boundary layer equation, we have the inertia terms u times ux plus v times del u del y equals nu times del square u del y square. So in this equation, at the wall, we have u and v to be 0. So which implies the double derivative of u at wall should be equal to 0. So that will give f double prime equal to 0 at eta equal to 0. So we have multiple conditions. So we can also put other conditions that the double derivative should be equal to 0 at eta equal to 1 and so on, so on, so on. And then these values will keep increasing. So we'll get more and more equations and you will solve for the values of APC from each of these equations, which is kind of, I think, is already discussed in the problems that are discussed in the fourth module of this week. So I'm not going to do that again. I've already given you the value directly. Let's take another velocity profile, say something like sine pi by 2 times y by delta. First check whether the boundary conditions are satisfied or not for this particular velocity profile. So the equation is f of eta. Is this a valid velocity profile? At the wall, eta is 0, so f is 0. At free stream, eta is 1, so sine pi by 2 is 1. So these two conditions are satisfied, and the derivative of this is cos pi by 2 times eta, e times pi by 2. At eta equal to 1, cos pi by 2 is also 0. So the three main conditions that we need, the no slip and zero shear and free stream velocity, all these three conditions are satisfied. So this is also a valid velocity profile. So there are multiple possible profiles for a given thing. So this is one kind of a limitation with this method. You do not have any basis as to choose which one over the other. You always need to compare it with your experiments. So you assume a profile, compute the values like the shear stress or something else, and then compare these values. If they match, otherwise they do not. And in any way, just because some particular profile gave you a better match doesn't mean that the velocity profile that really exists is that particular velocity profile. So this is meant to be an integral one, like approximate method only. Now, how do I solve for the boundary layer thickness from this equation? So we again use the momentum integral method where we have rho infinity square times d delta double star by dx is given by wall shear stress. So how do we compute each of these terms? Delta double star is the momentum thickness value and tau w is the wall shear stress. So first step is tau w. How do I calculate tau w? We have the wall shear stress given by at y equals to 0, and this I can write as mu times f prime of 0 times del eta by del y, where eta from here is y by delta. So del eta by del y is 1 by delta. This is mu infinity by delta times f prime of 0. This is one equation. And then now we also need to compute delta double star. As I already said, delta double star by delta, then compute as 0 to 1, f times 1 minus f theta. So then you have to equate these two equations and solve. So maybe first you can tell me these values, this value and this value, and then we will solve that. And nowadays you do not have to do this with hand calculation. If you have a calculator, you can do in a calculator. Otherwise, if you are familiar with Python, you can actually define this function and then you can use the SciPy module. There is a SciPy module for to integrate a function and it will give you the answer. But anyway, since in your exam you might be expected to do this with your hand, it will be a practice for you also to do it with hand. We, can actually do some transformation where you can consider pi eta by 2 as t and then this will become in your was with integration anyway, so I'm not going to spend much time on the derivation. So once you do that, that would eventually come to this. Can you confirm if you're also getting the same? Yeah, basically take sine square t as 1 minus cos 2t by 2, and then you apply the integration, then you will get this step. Similarly, on here, f prime of 0 is the derivative of this pi by 2 times this one. This will give me pi by 2 times mu infinity by delta. So once I have these two terms, then what I will be doing is substituting them in the momentum integral equation, which is equation number 1. So I have rho u infinity square times d delta double star by dx, which is 4 minus pi by 2 pi times d delta by dx equals tau w, which is pi by 2 mu infinity by delta. So if I rearrange this, I have something like 2 pi square by 4 minus pi mu by u infinite. I've just added this 2, so I can write this as ddx of delta square. And once you solve this, you have delta to be 4.8. You write it as delta by x. If you just evaluate this value and then take square root, so that comes as around 4.8. And from the Blazer solution, we already know that this actual value of this from the exact solution is 5. This is just meant to be an exercise where the idea is you start with the F equation, y by delta to be eta, and then all you have to do is calculate two terms. First, you have to calculate the wall shear stress, which is given by this equation. And second, you have to calculate the momentum thickness. Once you have both of these terms, you'll have to substitute them into the momentum integral equation. And then you will get an equation of this kind. So only this value will keep changing depending on the profile you choose. And then from there, you'll directly get the expression for delta. Now, once you have the expression for delta, remaining everything is straightforward. So I can substitute this delta back in this equation, and that will give me wall shear stress, from which I can calculate the spin friction coefficient. Now, the same method also you can do for delta T, again, Prandtl number greater than or less 7. All of that is again more of an exercise. So, which I'm not again taking up. So, I think this is pretty much clear. Are there any questions in this? Similar problem is also discussed in the lecture videos. So, if you have any doubts, we can discuss. Pretty straightforward. Then we can move to the next problem. Okay, then we'll move on to the next problem. This this is again to make you understand what is the difference between the average heat flux and how it varies as a function of x. Or we take an isothermal flat plate at determine analytically the position x where you have the average heat flux being equal to the local heat flux. So for an isothermal plate, we have the Nusselt number equation given by this is the local Nusselt number. Now we define two quantities, Qx, this is the local heat flux, and Q bar is the average heat flux for the total length. So the question now is, first question is, how does Qx vary as a function of x? So this is my Q double prime and this is my x. What will be the profile look like? Will it increase as function of x? Will it decrease as a function of x? How does it look like? You can recall, like in a couple of weeks back, we discussed that QW and shear stress both are inversely related with the boundary layer thickness. As you go along the x direction, the boundary layer thickness will keep on increasing. So if the boundary layer thickness increases, then the shear stress as well as the heat flux, both of them will reduce. So QW prime will have something like this. To get an exact relation, you can calculate from this. The Nusselt number is given by, or you can write Q double prime, the local heat flux, as the Nusselt number times the heat flux, that is because of conduction. Nusselt number is convection to conduction radiation, the ratio of convection to conduction. So Nusselt number times the heat transfer that would have happened if there was only conduction, which is K times, I'll just write delta T because this is isothermal and free stream temperature is not changing. I can write it as delta T by X. Note that I'm using NUX as with respect to length, so I will be using the same length here. If it was different geometry, then it would change, which is something that we'll discuss in the upcoming weeks. But for now, the local heat flux is given by this expression. And this Nusselt number, we can use the relation, have 0.332 times Reynolds number times Prandtl number, K delta T by X. So from this, we can write Q double prime of X, some constant times x to the power minus half. So this is the local heat flux. Now how do I get the average heat flux? Over the total length is defined by this expression. So if you solve this, what will be the equation you are getting? So there is a minus half. So if you integrate it, you will get a 2 times C1. And instead of x, I'll be having L to the power minus half. So the question now asks, what is the position x at which you will have both of them to be equal to each other? So we'll have to solve for q double prime x equal to q per L. So if you do that, we'll get x to the power minus half as 2 times L to the power minus half. So this implies x equals to L by 4. So at x equals to L by 4, if this is the total length, this would be my q bar. I think this is fairly straightforward. Now let us do the second part. For example, instead of the local local heat flux, what would be the value of x at which the local Nusselt number will be equal to the average Nusselt number? Can solve that part. That is also fairly straightforward from this. So have the local Nusselt number given by some constant C2 times x to the power half. So Nusselt number keeps increasing as you move away from the wall. Sorry, as you move away from the leading edge. And the mean Nusselt number is given by, this is the only difference that needs to be highlighted here. The mean Nusselt number is defined in this particular fashion where you have to integrate it, the Nusselt number divided by x to the px. This is coming from the fact that you have to use the local heat transfer coefficient. In order to calculate the mean Nusselt number, you have to first calculate the mean heat transfer coefficient and then you have to calculate the Nusselt number from that. So this versus there is other way that normally this is another common mistake that sees even in our college is this. So people actually use this relation to calculate mean Nusselt number, which is not that way. It's we actually the mean Nusselt number is actually defined in this particular fashion. So difference is because you first start with the derivation of mean heat transfer coefficient. The mean Nusselt number is defined as the mean heat transfer coefficient times the length by k. So we have to calculate the mean heat transfer coefficient first, and then from there we have to calculate this, where the mean heat transfer coefficient is given by this definition. So if you substitute that back there, nu L bar will be 1 by L will get cancelled. So we have integral 0 to L hx dx, where the local Nusselt number, local heat flux heat transfer coefficient is given by nu x by x dx. I can do this now. I think this part is clear. So the point I'm trying to make here is do not use this relation. Use this relation and compute the average Nusselt number. If you do that, I'm getting this around 2C2 square root of L, which is basically 2 times the Nusselt number, local Nusselt number evaluated at x equal to L. So from this, if you calculate the same problem as we were doing before, what is the value of x at which the local and mean Nusselt number will be equal? So if you substitute NUX equals to NUL bar, this would give us x equals to around 4L, which means that the mean Nusselt number, the local Nusselt number will be equal to mean Nusselt number far downstream to the length of it. So it will be like 4 times the actual length. So it will be way farther downstream. While heat flux is around L by 4. Yes, the point that I would like to highlight is this particular definition in this problem. So do not do this mistake of doing this. Even when later, after this, you will eventually, like by the end of this course, we will see that most of the problems, like the ones that we are discussing a flat plate, are simple enough that we can solve. But eventually, as the geometry gets complex and complex, there will be so many features, and we'll have to move to CFD, computational fluid dynamics. And once we move there, first we will have to benchmark our course against these sample cases. So then we'll have to compare the results from our simulation against the experiments or any of the results that have been reported in other literature. Then most of the literature uses this particular definition. So once you get the simulation data, usually when you calculate Nusselt number, you have to make sure that the particular whatever code you are writing to calculate the mean Nusselt number should not be using this definition. Instead, it should use the other definition. Only then your values will match with the other literature. This is to highlight that particular point. Are there any questions? Okay. Yes, there are no questions. We'll take another problem. This is slightly different from the boundary layer theory that we have been discussing, but still it makes use of the integral formulation. So that you can understand where there are other avenues where you can actually use the integral formulation that have been developed specifically for this, like discussed in this particular lectures. So let's consider this problem where you have a jet coming with a uniform velocity u naught. The initial thickness is d naught of the slave. So as the jet comes from this, you can consider this as a nozzle spray that is coming. So once it comes out, it will start expanding in this way. So it will, as it expands, the diameter at any particular x location, x is the direction of the flow, at any location is given by dx. And at the dx, now let us assume for simplicity that you have velocity profile only like this. So at the center, you will have maximum velocity. As you go farther away from the center, the velocity reduces to 0. The question now is to determine the order of magnitude of d and u in terms of d naught and u naught, or to put in other words, you are supposed to find what is the order of magnitude of d by d naught and u by u naught in terms of x and u. So if you non-dimensionalize them, so first for this problem, what are the non-dimensional numbers? So we have discussed this in week 1. Whenever you have a problem like this, without any buoyancy terms or anything, the non-dimensional number that will be governing that particular problem is Reynolds number. So in this case, Reynolds number with respect to the free stream velocity, this and the property. So one non-dimensional number we'll be having is u naught d naught by nu. So let's call this this is our Reynolds number. So this is one non-dimensional number for this particular problem. And then we have geometry number. So x will be scaling as x by d naught, y as y by d naught, and u as u by u. So these are our non-dimensional variables. So now from here, how do I do the order of magnitude analysis? This we have done for boundary layer theory. This is just to kind of again reiterate the same thing so that you can apply this in other domains also later. So where do I start to do the order of magnitude analysis? We have only two kinds of equations, the continuity and the Navier-Stokes equations. So we'll start from the Navier-Stokes equation, and I'm already making the simplification here that I'm saying the that we are sufficiently long away from the slit, which essentially means that the diameter of the jet that we are getting here is much smaller compared to the length from the nozzle. So which means I can use the bound, just like in boundary layer where we did that delta by L is very much less than 1. This is the assumption that we used in boundary layer theory. So similarly, what I'm trying to say now here is dx by x is very much less than 1. This is the first assumption that we are making. Once we do this analysis, then we know that we can use the boundary layer equations. So this is just like, so the boundary layer equation will give me the inertia terms, u times del u del x plus v times del u del y is mu times, I'll use the non-dimensional quantities. So I'll have u naught d naught times del square u del y square. Okay, take this u and v as non-dimensional velocities, x and y are also non-dimensional distances. Then this will be my governing equation. So now I have to do, again, this is happening because the del square u by del x square order of magnitude will be 1 by x square. And since we know dx by x is very much less than 1, I can ignore the other derivative. So this is the boundary layer equation. The only difference between this and the boundary layer equations that are discussed in the lecture videos is that in the boundary layer, we have a solid wall at the bottom, so that at y equal to 0, we have velocity to be equal to 0. But in this particular problem, at y equal to 0, velocity is maximum. That is the only difference. So that wouldn't affect the governing equation. It would only change the boundary condition anyways. So now if you want to do the boundary, the order of magnitude analysis, what is the order of magnitude of the first term? So for u, we'll scale as u by u naught. Again, we have u, so this will be u by u naught square. X scales as x by d naught. So this will be for the first term. For second term, v will also scale as, how will v scale? How will I get the scaling of v? What did we do in the boundary layer analysis? So one is the Navier-Stokes equation. The other equation that we have is the continuity equation. So from the continuity equation, we can write as del u del x plus del v del y equal to 0. So from this, we can get the scaling for v. So u will scale as u by u naught. X will scale as x by d naught. So I'm writing it as d naught by x. This should be same order of magnitude as del v del y. We have v scaling as something divided by d naught by y. Instead of y, I'll write it as d. So from this, we get v scaling as u by u naught times d by x. This is a scaling for v. Now if you take our equation, so v would scale as u by u naught times d by x. Again, we have a del u by del y. So you would again, we have another u by u naught times y will scale as d by dt. This entire thing is essentially u by u naught square times d naught by x. So both the inertia terms are of the same magnitude, which is something that we got even in our boundary layer equations. Now what about the diffusion term? How will this scale? We have nu by u naught d naught, and then we have del square u del y square. U will scale as u by u naught, and y scales as d by d naught. So this will be d naught by d whole square. Now we know that all of these terms are important, so all of them have to be of the same order of magnitude. So that gives us. So from this we can write u by u naught square times d naught by x should be of the same order of magnitude as the term here, which is u times u by u naught square, then d naught square by d. So from this, I can write u by u naught. And then I have a d here. Okay, there is a square, d square. So I have d by d naught square. And I'll take all other terms on RHS. So that will be x by d naught. And then I have extra u naught here. And there will be a d naught divided by nu. Is this clear? So we know from the momentum equation that the product of u by u naught and d by d naught square should scale as x by d naught to the divided by the Reynolds number. But the actual question that we are trying to solve is find the individual scales of u by u naught and d by d naught. Now, how do I get that from here? Once that is done, then this problem is kind of solved. Maybe I'll wait for a minute. You can tell me how I would go about doing that. So we need to know something more about this particular case in order to determine the individual scale. So like we know that the product of these two things is a quantity, but in order to understand what is the scale of each of the individual terms, we need one more equation. So how do I get that one more equation? Now we will do the same thing that we did for boundary layer theory, where we convert this into an integral equation. So let us do an integration for the momentum equation from minus infinite to infinite. Can you do this one and let me know what? So once you do this integration, and then you tell me what you're getting from this. So in the when we solved it for the with a flat plate, we got the momentum integral equation. But here the difference is at wall, we do not have any wall here. That changes something. So what would that change and how would that influence the final result that we are going to get from this equation? Because when you have a wall, we have tau wall. But now I'm saying that here we get maximum velocity, which means tau wall is 0. So if tau wall is 0, then we do not have any equation at all from that. So which means something is getting conserved here. What is it that is getting conserved here? So like in the case of flat plate that we were solving in lecture videos, there is a shear stress that is happening at the wall, because of which energy is getting continuously lost. But here we do not have anything like that. So something is getting conserved here. So that is what you will be getting once you do the integration across the entire domain. At any given x, what we are doing is at any particular x, we are integrating from minus infinite to infinite. So once you do that integration, you will conserve something. So in order to get that conservation quantity, we are doing the integration of the boundary layer equation that we have from the Navier-Stokes after we did the scaling analysis. So you can do this integration and tell me what is the quantity that is getting conserved. Is the idea clear? Till here, are there any questions? Being like 1 hour into the session, if you want a small break, you can take a little break. Oops. Well, wait for a couple of minutes. You can try to solve this integral and tell me the quantity that you are getting once you solve the integral. If you have any difficulty in solving that, you can chat or you can unmute yourself. So that way I can understand whether you're able to understand something or if there is any gap between what I'm trying to discuss and your understanding. Are you able to get some equation? Or maybe we can do term by term. So let's say we'll start with one term. First term we can do just like what we did in boundary layer equation. So this term will essentially boil down to something like, just take the u inside, so put half times del u square dy. Second term, you can apply the integration by parts, so which will give me v times u minus infinity to infinity del v del y times u dy, and this will give me mu times u naught d naught del u del y evaluated at infinite and del u del y evaluated at minus infinite. So how do you proceed from here? So in the boundary layer theory, when we solve it, it's from 0 to delta. So there we have v delta being not equal to 0. But however here at both plus and minus infinity, this particular quantity will go to 0. And what about this quantity? Sorry, this quantity. Even the if you see the velocity profile, it goes to 0 at both plus and minus infinity. So the derivative also goes to 0. So both these terms also tend to 0. This and this also go to 0. And minus del v del y, we can write this as, the first term will remain the same, half del u square del x. And from continuity, we can write minus del u del y as del u del x times u dy from minus infinity to infinity. So if you just take this two, so this essentially gives me, and then you can apply the Newton-Leibniz rule, and that gives you which essentially means the total kinetic energy or the total momentum is actually conserved. So because there is no wall, in between, which essentially boils down to saying there is no shear stress, so the net force is zero, which means the total momentum that you are going to get integral rho u square, like rho is constant, so I've taken it out, u square dy equals to zero. So this you can, instead of doing like this, you can start from the momentum integral method and then do. So where we have tau w given by rho u infinity square times d delta double star by dx. So if you start from this equation, where we have delta double star as by delta, or delta double star, right, as integral 0 to delta. So this would be the case from 0 to delta. If it were from minus, like this equation itself is not valid because this term will be 0. So we know that the momentum thickness has to be constant in some way. And this term kind of is something quantity, this quantity is something that is reflected, that is kind of shown in this particular way. So this is the delta double star in case when you have both sides, like in case when you have something like this, where you have a symmetric jet that is developing in both the directions. So it is kind of like a boundary layer only, but then we do not have any shear stress at the center line. So this is conserved. So what can I say from here? So the magnitude of u is u by u naught square times this will be d by d naught. Y is d by d naught is some kind of constant. Sorry, this is not zero. This is some constant. So I'll just say it would scale as of order one. So this is one equation, and then we have one more order of magnitude, which is this. So now we have two things. So from these two, you can determine what is order of magnitude of u by u naught and d by d naught. That is fairly straightforward. So you basically have to square this equation. So that will give you u by u naught to the power 4 times d by d naught square is of order 1. And d by d naught square is this one. So you can substitute that back and you will get u by u naught scaling as x by d naught, d naught by nu, whole to the power. So you have power 4. This will have minus 1. So minus 3. So this will be minus 1 by 3. And square of this should be there. So you'll have the same quantity. Square is minus 2 by 3. So this will be plus 2 by 3. Is this clear? So unlike our, now we know what the scaling is. So from this scaling, we can decide what kind of profile to use and how to determine this thing, other stuff. So previously, for example, when we are solving the boundary layer equations, so this d by d naught is something like, so from this you can also get the scaling for d by x. Reynolds number to the power minus 2 by 3. So from this you can write the scaling for d by x as x by d naught power minus 1 by 3 times Reynolds number to the power minus 2 by 3. So the d here is basically the diameter of this, which is something that you can relate with the boundary layer thickness that we were discussing for the flat plates. So delta by x is something like this. So in the boundary layer case, we have delta by x scaling as x to the power minus half, but here it is scaling as x to the power minus 1 by 3. And other scaling relation. Now this is just for the momentum thing. So now let's say if temperature is also there. So we have T infinity and the jet is coming at a different temperature than the ambient temperature. Then how would that changes this thing? The same analysis. You would start from the energy equation and then do something similar like this, from minus infinite to infinite, and then you get the energy equation values, where you get integral u times T dy equals to constant. And from there you can determine what is the scaling for the temperature as a function of x and so on. Uh, which I leave it as exercise. So this is an exercise problem taken from page and textbook. So whoever is interested can actually look up the textbook for the detailed discussion of the problem. If you have any queries, we can discuss the problem. But are there any questions? Is this clear? This is another way where we can use the integral method. to come up with some kind of conservation laws over the entire domain, and from which we can do our scaling analysis. There any questions? If there are no further questions, then we'll move on to the next problem. Yeah, this in the beginning we solved the momentum integral equation. We did not actually solve the energy integral equation. So this problem is where you can solve energy integral equation. So assume laminar boundary layer over a wall with uniform heat flux and Prandtl number equal to 0. Like it's not really 0. It's like you can assume this to be like Prandtl number very much less than 1. Determine the correlation for local Nusselt number using integral method. So how do we do this? First thing is we have to assume a temperature profile. That is where all these methods start. So what kind of temperature profile can I assume? So but even before that, what does this assumption mean? What happens when Prandtl number is very much less than 1? So if Prandtl number is nu by alpha, which will be delta by delta t, and I'm saying this quantity is very much less than 1, which means delta is very much less than delta t. So how do we visualize this? Is you have some flat plate which is having a uniform heat flux. Q double prime is constant. And first, let's say the boundary layer develops, velocity boundary layer develops, and then the thermal boundary layer is also there. So we are saying delta is very much less than delta t. So this is the velocity boundary layer thickness, and this is the temperature boundary layer thickness, the thermal boundary layer thickness. So if I write my energy equation, which is U times alpha is the thermal diffusivity times the diffusion. So this is the diffusion term and the inertia terms. This is the thermal boundary layer equation. Now, if under the particular case when Prandtl number 0, it essentially means Prandtl number is very much less than 1. We have delta being very small, less than delta t, which means the velocity profile will be, if at any point if I take the velocity profile, it will only vary very little here, and after this it will be more or less constant, right? So for most of the region, velocity is basically constant, and if Prandtl number is exactly 0, then this delta will become 0. So we'll be having just the free stream velocity everywhere. So which reduces the complexity of our problem. So this problem will essentially becomes U infinity because delta is very small than delta t, and this boundary layer equation is valid in the entire region, in this entire region. And in most of this region, the velocity is constant. So we are taking U to be equal to U infinite, del t del x, and V is 0 in the free stream. So that will be alpha times del square t del y square. So this will be the governing equation that is for this particular problem. How do I get exact solution for this equation? I think you are from math department, right? So you recognize this equation, right? So how do I solve this equation? Like what is the solution of this equation? something similar also is there, right? So I can rewrite this equation a little. So if I write this as this is kind of discussed in most of these partial difference equations. If maybe you might have seen it in a different form, you have something like del f del t is some constant times del square f del x square, something like this. And the solution of this is an error function depending on the kind of initial and boundary values that the initial conditions you're having. So this is also the type of equation you will get in case of steady state conduction for a semi-infinite slab. Just that x is replaced with time. So we are marching in space instead of time. That's the only difference. But anyway, now we will be solving we will not be using any exact method to solve this. We will actually use the integral method that is discussed in this particular week to solve this particular problem. So how do I use that? So what is the first step to solve? Like we have this equation, now I have to use an integral method. So what will I be doing? The first step would be what? First, I have to know the boundary conditions. So what are the boundary conditions that are given to me? Steps are straightforward. First, I have to assume a temperature profile. And then use boundary conditions to determine constants in that profile. Except for delta. So we need one more equation for delta and then use energy integral equation. Right? So what is the profile that I'll be starting with? So what are the boundary conditions first for this particular problem? So for an isothermal wall, we can use that at y equal to 0 equals to wall temperature, but we do not know the wall temperature here. That itself is an unknown. So the boundary condition that is given is the heat flux. So minus k times del T del y at y equal to 0 should be equal to the wall heat flux. That is one condition. And then we also need, we have the free stream temperature beyond delta. So at y equals to delta, it's actually delta T. Delta T. This should be equal to the free stream temperature. Let's say T infinite. And then what other conditions do I need? That beyond the boundary layer, temperature should not be varying. Like beyond the boundary layer, temperature is free stream temperature, which is T infinite. So if I go along y direction, the change should be 0. So that would be del T del y at y equal to delta T should be 0. So I have three conditions. So if I'm trying to solve it as a polynomial equation, then I can have only three unknowns. So the profile that I should be taking is a quadratic one. So I'll take a profile of the form T of y is a plus by, sorry, again we are assuming self-similar nature. So this will be b times, or I'll just write it as by and then you will eventually get that expression. Now b and c will be in terms of delta abc. So I can write like this. Now you can solve, substitute these boundary conditions, get the equation and solve for abc. This is first step. Now solve for ABC. Maybe I'll wait for, this might take some time. So maybe 5 minutes. You can solve this and tell me the value of like what is the temperature profile that you are getting. expression. So I'm getting this as t infinite plus something like this. So once you have this expression from here, this is straightforward. So you basically define your t minus t infinite by this quantity as 1 minus eta square, where eta is y by delta. And then now all I have to do is solve the integral formulation. So I'll have to start from this equation. So my equation is del t del x is alpha by mu infinite del square t del y square. So the first step is I have to do the integration from and you can actually take the energy momentum integral that I have already defined. That will be straightforward. So we know that the energy integral equation is d dx of 0 to delta u times t minus t infinite dy should be equal to q all by rho cp. So we already derived this equation before. Instead of rederiving the equation, the only difference now is previously we have u as a varying as a function of y, but now we know that we know that delta t is very much greater than delta, so we can replace this u with u infinite. So then we'll be having u infinite times d dx of integral 0 to delta t minus t infinite, delta t. I think that was a mistake even in the previous one. So this will be delta t everywhere. From here it is straightforward. We know t by t minus t infinity from this. So I just substitute that back here. So that would give me q double prime times u infinite by 6k times d dx of, after doing the simplification, I'll get something like this. After I do this integration and substitute that into this one. So from this, this is straightforward. I can directly calculate delta t. Or I can write this as, so instead of Rayleigh number, we'll now be having Peclet number here. That's the only difference. Previously, we used to have Reynolds number here, but now this is a Peclet number. Once I have this delta t, how do I calculate Nusselt number? Nusselt number is defined as convection to conduction. So convection heat flux is q double prime W. Conduction heat flux is k times delta t, which is t wall minus t infinity. I have to replace this with x. And now I have to calculate tw minus t infinity, where tw is basically t at y equals to 0. So if I substitute y equal to 0, eta will be 0. So from this equation, I can get tw minus t infinite. That will give me q double prime x. I'm not using w. A times q double prime delta t by 2k. So this gives me 2 times x by delta t. So I can substitute that back here, and that will give me around 0.816 times square root of inverse of this, so you infinite x by alpha. So this is what I'm getting from integral solution. Now, like I said, you can also do the exact method. So you know how to solve this equation. The solution of this will be an error function. like in terms of error function, from which also you can do the same process. You get the temperature profile. From the temperature profile, you can calculate minus k times delta del y at y equal to 0 and get the Nusselt number from there. Once you get the Nusselt number, then compare this coefficient. Maybe I'll leave that as an exercise. And then find the local Nusselt number, compare with the integral solution. So just like what we did for the momentum integral, we started deriving the Nusselt number and then we compared with the places solution. Similarly, for this simple problem, you can solve like basically you have to introduce a parameter here. The only thing is now you have to introduce a parameter eta, which will be y times square root of alpha x by u infinity. Once you introduce a parameter like this, and then from there you'll have to get the similarity equation for this. So you do the variable transformation like eta and x are given, so you can write this equation, like, and then convert this entire equation in terms of eta. That will be a ODE, which is again that ODE is very simple to solve. You can solve that ODE, and once you get the solution, calculate the local Nusselt number from that. I think this comes around 0.88 or something. So there will be some 10% or 8% error in this. You can compute and then check yourself. If you have any doubts, you can write to me on my email, or you can post it. You can discuss in the next session. So when we meet in the next day. Are there any questions in this? Okay. I think we have done enough of analytical ones. So maybe now we'll solve some numerical problems where it's more about using the relation directly and solve it so that you do not have to do the integration, etc. So let's take a simple one first. A rooftop flat plate solar collector measuring 1.8 meter by 2 meter long is mounted horizontally on a building. The top surface absorbs solar radiation at a uniform rate of 200 watt per meter square, and surrounding ambient is at 30 Celsius. A steady light breeze at 3.3 meter per second flows parallel to the 2 meter length of the panel. Assuming the back surface of the panel is perfectly insulated and the radiation loss to the sky is negligible compared to convection, determine the equilibrium temperature of the solar collector surface. So I have a surface like this. This length is 2 meter. This or drawn it proportionally. So this is 1.8 meter, and wind is blowing in this direction, parallel to the 2 meter surface. The value is given as 3.3 meter per second. Temperature is also given. So U infinite is given as 3.3 meter per second, and T infinite is also given as 30 Celsius, which is 303.15 Kelvin. So now the question is to compute the final temperature of the average temperature of the surface once it reaches equilibrium. So we know that it reaches equilibrium. So the net heat flux that is absorbed should be equal to the net heat flux that is rejected by convection. So the net heat absorbed is Q double prime is given as 200 watt per meter square. So at equilibrium, we need this Q double prime should be equal to H times the average surface temperature. I'll call that as Ts minus T infinite. How do I get the H value? Which is again average value. This is also average. So how do I get the average heat transfer coefficient? So we'll have to use from the Nusselt number. So this I can write this as, this is the convective heat flux, which is Nusselt number, the average Nusselt number times the conduction kappa times delta T by the length. So in this case, length flow is parallel to this 2 meter surface, so length is 2 meters. And now for the only problem now is I need to know the correlation for Nusselt number. Maybe I will give you the correlation. So what is the correlation for Nusselt number in this case? This is an it says that it is a uniform heat flux. So for uniform heat flux, we have a different correlation from isobarnol one. So for uniform heat flux, I have Nu bar. The average Nusselt number is given by this particular correlation. And for now, take Prandtl number as 0.71. This is something I think we discussed in last week, and I told you that we will discuss a problem on this in this week on this particular case for isoflux case, because last week we solved isothermal problems. So the first concept is, in order to calculate Reynolds number, we need to use U infinity times L by nu, where nu is the kinematic viscosity. For air, nu is given by the expression, or I'll write it as rho by mu, rho infinity L by mu. For air, you can actually assume the density as ideal gas equation. So pressure, P atmospheric pressure, times the molecular weight divided by the gas constant times temperature. So this is P atmosphere. You can just write the values here. So atmospheric pressure you can take as 101325 Pascal. Molecular weight is can take 28.97 gram per mole, and R you can take it as 8314 joule per gram mole. And temperature is the temperature that we'll discuss what the temperature is. Now similarly, viscosity is also a function of temperature, which is again for air given from Sutherland's law as n power minus 6 minus 5 . So the only problem now is what is the temperature that I should be using here. So for an isothermal case, we discussed the concept of film temperature, where you define the film temperature as the average temperature of the surface and the free stream. So once the film temperature is known, you substitute that film temperature here, get the mu value, get the rho value, calculate the Reynolds number, and from there you can calculate the Nusselt number. But in an isoflux case, the Ts is an unknown. Because Ts is an unknown, we cannot calculate the film temperature. So this is where we have to iterate. So this is something that I kind of briefly discussed in the last week, but we didn't solve any problem. So this week we'll actually solve one problem with this. This is also quite straightforward. So all you have to be doing, maybe I'll copy these equations here. So we have rho equation, T equation, and Nusselt number. We will take everything possible. So first we have to assume a film temperature. So from the film temperature, we will calculate nu value, where nu is basically mu by rho. The kinematic viscosity is the ratio of dynamic to the density. So assume a TF value, substitute that into this equation, get the mu value, substitute this in equation, get the rho value, then calculate mu by rho. Once you get the nu value, you can calculate Reynolds number. And from that Reynolds number, you can substitute in this equation, Prandtl number take 0.71, and you can get Nusselt number. Once you get Nusselt number, we need to calculate Q double prime. So we need to calculate TS. So TS, in order to calculate this TS, I have Nusselt number. So I still need to calculate the value of kappa. So thermal conductivity, you can calculate from the definition of Prandtl number, mu Cp by Pr. We already know the mu value at that particular film temperature. Cp, you can take it as 1006. Prandtl number is 0.71. That will give you kappa value. Once you have kappa, so this is the equation we will be using. Q double prime is already given as 200. So you can substitute 200 equal to this, and from there you can calculate the value of Ts. So first you calculate the heat transfer coefficient, and from the heat transfer coefficient you can calculate Ts. Once you calculate Ts, then what we will be doing is using that Ts, we can again calculate Tf. It's like half into Ts plus T infinity. Maybe I'll write the equation for Ts also. Ts is basically T infinite plus Q double prime by H. and H is basically from this equation you can get. Is the workflow clear? Now what we will do is the TF that like you initially start with an history guess for TF. From that calculate your thermophysical properties, calculate Reynolds number, calculate Nusselt number. Maybe I'll okay fine. Can change this order. Once you calculate the okay, this was a change. Yeah, first at the assume a film temperature, calculate all the thermophysical properties mu, rho, kappa, etc. Then calculate Reynolds number. From there, calculate the Nusselt number. Once you have the Nusselt number, you can calculate the heat transfer coefficient. From there, you can calculate the surface temperature using this relation. And once you have the surface temperature, again you can calculate the film temperature. This film temperature should be equal to this temperature. If it is not equal, then you'll again use this film temperature, again start from here. Again do the same process. You do keep doing this till the value here and here are within a given tolerance. And once you reach that tolerance, then you will know the surface temperature. For an isothermal case, it is only one loop, but for an isoflux case, we'll have to do this. So let's say you start with an assumption that this is 30 Celsius and then calculate all these values. I think you can try this out in an Excel, which is much faster. If you do it in Excel, it will be straightforward. You'll have to put this formula and then do it. Or if you're familiar with any programming languages, this is actually very straightforward one. I've done this one, so I'm getting the values of around 1.598. You can cross check this later. -5. The inner conductivity is around 0.02637. I got Reynolds number around 413090. This is another check. Once you calculate the Reynolds number, you have to make sure that you are within the laminar region. Otherwise, this particular correlation itself is not valid. So this is less than 5 into 10.5. So I am within the laminar region. So I can use this correlation and calculate the Nusselt number, which comes out to be around 579.48. Once I have the Nusselt number, I can calculate the heat transfer coefficient, 6.848. From the heat transfer coefficient, I can use this relation and calculate the surface temperature. So that comes around, I got it in Kelvin, 332.35. And now I have the T surface temperature, and maybe I can write this also in Kelvin. This is 303.15 Kelvin. So this and this values are in Kelvin. So I can take the average of 332.5 and the ambient temperature. So that is giving me around 317.65. So you can see that I assume something, but then the value I'm getting here is not matching with that assumption. So now I'll have to redo the calculation again. So I'll start with this calculation now. So I'll start from 317.65 and then again repeat the same process. I'll calculate the thermophysical properties first. So these values. The Nusselt number. Again, this is also less than 5 into 10 power 5. So I can use the laminar assumption. From this, the heat transfer coefficient. And from there, the surface temperature. And from this, I can again calculate the TF value. So you can see that now this value sorry, this is TS. So this value is TF is coming around 370.83. So I started with 317.65 and it became 317.83. So the difference is less than like 0.2 Kelvin or something, which is acceptable tolerance for me. So I'm stopping here. But you can also perform one more iteration starting from 317.83 and then you can actually check that this value actually goes in very close to this. The error will be like 10 power -3 or something. Like only the third decimal place will change. So, but now that you can see that this value is close to this value, so that is when you stop your iterations. Like I kind of gave the numbers in such a way that it stops after 2 iterations, but in reality, in some problems where you have very high heat flux values, you might have to do multiple iterations. The point is that the workflow is clear. Are there any questions in this? For most of the cases, usually like with air or something, you usually assume constant properties. So you do not have to use these complex relations, and then that kind of simplifies the problem. But depending on the temperature range you are working, this can actually be important. In this particular case, this particular value, if you convert to Celsius, this comes to around 59.86 Celsius. So the solar plate that we are discussing, the surface temperature can actually reach close to 60 Celsius. So from 30 Celsius to 60 Celsius, you have a difference of around 30 Celsius. So the properties in that 30 Celsius range is actually like the error that you get from that. So using this new value, you can actually compute mu of t equal to 60 Celsius minus mu of t equals to 30 Celsius. You can compute this difference and then see what happens if you assume just 30 Celsius and compute this percentage error. Then you'll understand how much property changes are there. This is where we are, that is why we are using, and from there we are actually using the average temperature of this. So this is actually the film temperature, right? This is around 59.86. So instead of using either 60 Celsius or 30 Celsius, we are actually using an average of both of them. So the film temperature is actually average of 60 and 30, that is around 45 Celsius. So we are using a film temperature of 45 Celsius. So you can actually calculate the error with respect to that also. So you can calculate this replace with 45. And you can calculate the percentage error you're getting from this. Similarly, you can also do the other way around. So mu of t is 30 Celsius minus 45, sorry, and see how much error you're getting. So essentially, as a function of temperature, your viscosity reduces. So this is at 60, this is at 45. But instead of using either of these values, sorry, this is at 30. So instead of using either of these values, we are actually using somewhere here at 45. So the deviation that you are going to get will be plus or minus something. If you use only this one, let's say the error is 5%, plus or minus 5% if you use 45. If you use only 60, then it will be minus 10%. If you use only 30, it will be plus 10%. So instead of that, we are using the mean temperature so that our error will be symmetric around that mean value. So it will be plus or minus 5% or something. You can actually calculate this percentage values and see. And then you can also experiment then that instead of 60 Celsius, let's say this becomes 100 Celsius. Then you can see that how the error actually increases. And then you'll understand from there you will estimate like you'll get an understanding, okay, if 10% accuracy is acceptable for the particular problem that you are solving, then you can assume the constant properties. If for example you encounter a scenario where the temperature is let's say 100 or 120 Celsius and the error estimate that you're getting from this is let's say 20% and which is not acceptable to you, then you cannot use a simple film temperature and then do whatever we are doing here. Then we'll have to move on to something else. Or so that is the basic idea I want to make. Is that part clear? There any questions? We have around 10 minutes left, but I have one more problem, which might take little longer than that. I think I'll cover that problem in the next week, initial during the recap session. Are there any other questions that you want me to discuss? That you have any doubts or something? This we'll discuss in next week. Or you can also try this as an exercise. Give you idea of the problem, so you can try it out, and I'll discuss this next week again. So you have a transformer of given size, let's say this problem is actually taken from Angel textbook. So if you have the textbook, you can go through the textbook also. So this is given as the height is given as 5 centimeter. Let's take this as the length, 10 centimeter, and then let's take this as 6.2 centimeter. So this is some transformer block that we have, and it is cooled by an aluminum heat sink. So what this heat sink is like some extended surface. So you'll have some surfaces protruding from this, something like this. You might have seen a transformer having something like this. So essentially you have 7 fins. Okay, I've drawn only 5, so I'll just draw a cross section of this. So you'll be having this as the base, which is 5 centimeters, and then you have multiple 7 fins on top of this. So this is 5 centimeter. I've just drawn it not to the scale. The height of the fin is 5 mm. So this is not drawn to the scale. This is 0.5 centimeter. The thickness is 2 mm. So this thickness is 0.2 centimeter. And length is in the third dimension. So that is this length is 10 centimeter. So these are multiple fins. Now a flow is happening parallel to the 10 centimeter. So some air is blowing like this with some velocity u infinite. We are assuming that the entire surface is isothermal. So the entire surface temperature is 60 Celsius and the air is coming at 25 Celsius. If the total heat that has to be dissipated is 20 watts, so for this 20 watt, what should be the inlet velocity u infinity so that you can reach the 20 watt. This is actually same as whatever we were discussing. The only thing is you need to understand what is the total surface area that you have to consider. Like you first start with the Nusselt number correlation, the average Nusselt number, which is given by 0.664 times Reynolds number to the power half, Prandtl number to the power 1 by 3. So we know the Prandtl number, you can take it as 0.71, all the property values that I have given in the previous problem. Reynolds number is something that we need to find first. So you know the heat flux is 20 watt, you know the length of it, so you first have to calculate what is the Nusselt number, the required Nusselt number. From that you calculate the required Reynolds number. Once you calculate the required Reynolds number, you will have to, from there you can calculate U infinity. Again here the T infinity is given and T wall temperature is also given as 60 Celsius. So film temperature is straightforward, average of these two temperatures. So you can directly use the relation I gave for viscosity before, and from that you can calculate this new. Once you have the Reynolds number, you can do it. The only trick, like the only thing is you have to understand what is the area that is getting cooled, and from there you have to get the Nusselt number correctly. Once that is done, this is actually a straightforward problem. I will leave this as an exercise. We will discuss this next week again. Do you have any other questions that you want me to discuss? This is clear. To quickly summarize, this week the main concepts that we have been discussing is the concept of displacement and momentum thickness, which will give an idea of the mass deficit and the momentum deficit. And from there, we extended the concept same to the energy boundary layer, and we got another thickness for energy layer. From this, we have two different equations. One is the momentum integral equation, the energy integral equation, which relate the heat flux, the shear stress and heat flux respectively. Then we have discussed some problems on how to actually calculate something called a shape factor from the displacement and momentum thickness, which gives us an indication of the type of boundary layer we are having, laminar versus turbulent. And then we discussed some problems and applications of how to use the momentum integral technique to calculate the boundary layer thickness using an assumed velocity profile. Then we solved another problem on this is just to understand how to use the correlations that we already have and how to calculate the average Nusselt number in the way that is usually reported in the literature. The key point here is to understand that the relation is defined in this way and not this particular way. And then we discussed again, went back to the scaling analysis, and we actually saw a problem where we can use the integral technique to derive a conservative law. Essentially, in this case, we actually derived that in absence of shear stress, you actually have the momentum getting conserved. And this equation we obtained directly by integrating the Navier-Stokes equation. So we can actually use the integral technique that is developed in this course to derive some conservative laws of this kind and use that to determine scaling relations accordingly for different problems. Next problem we solve for a specific case where the Prandtl number is very much less than 1. In that particular case, the energy equation can be simplified to another equation. Again, we solve this using integral technique, and I left you as an exercise where you can actually solve this using the similarity variable, just like we did in the last week, where you define a similarity variable, get the like the Polhausen solution, you get an equation for it in terms of similarity variable. You can try that here, and then calculate Nusselt number, compare with the integral solution that you have here, and see how much error you are getting. You can see that the second method is actually more tedious, while this is actually straightforward. And then we have discussed one more problem that I promised last week, is where instead of uniform temperature, if you have a uniform heat flux, then Philip temperature is an unknown. So we have to iterate to get a solution. So where initially you assume a film temperature, from that calculate the thermophysical properties, and then your non-dimensional numbers, from which you calculate Nusselt number, then calculate the heat transfer coefficient, from which you calculate the average surface temperature, and again calculate the film temperature. If the film temperature that you're getting after doing all these calculations is different from the one you assume, you again start from this film temperature and repeat your process. Again, this here 2 iterations it's solved. You keep repeating till the temperature change in film temperature is within the acceptable threshold that you set for your particular case. And then there is last case of transformer cooling, which I'm leaving you as an exercise. We will discuss this as the first problem next week again. If you have any queries. Yeah, that sounds from my side. Yeah, if you do have any feedback regarding the pace of the session or the type of problems that I'm discussing, please do fill in the feedback form. I'll try to incorporate them for next week. Yeah, if you do not have any further questions, I think we can end the session for today. Yeah, thank you for joining. We'll again meet next week, same time from 5 to 7.